What if we could measure the similarity between two data points, but not in regular space? In a space so vast and complex, even classical computers struggle to describe it. Welcome to the world of quantum machine learning, where data meets the power of quantum mechanics. In this video, we are diving deep into two core concepts: quantum feature maps and quantum kernels. You'll learn how classical data is embedded into quantum states using feature maps and how quantum kernels compute similarly in a way classical systems simply can't. Today, we'll be discussing the topics: what is a feature map, what are quantum feature maps, how they work, steps in quantum feature maps, why use quantum feature map, classical kernel, quantum kernel and mathematical definition, high dimensionality data embedding, and their use cases. Firstly, what is a feature map? In classical ML, a feature map is a method to transform data into a new space, usually making it easier for models to separate, classify, or analyze the data. For example, mapping 2D data points into a curved 3D space can make a complex pattern simple to detect. If you observe in this 2D plane, we have two types of data. Let's say pink color data is one data and green color data is other data type. Here we can't use a linear line to separate both datas. But while plotting them in the 3D plane, we can say that they are linearly separable using one line. Now let's see what is a quantum feature map. It is a method that takes classical data like numbers from a dataset and encodes it into the state of quantum system. This encoded state can be exponentially rich, living in what's called a Hilbert space, a space that grows with number of qubits. How it is represented. This quantum state is represented as ket of phi of x. This acts like a fingerprint of the data, enabling quantum models to process, transform, and compare it in a ways classical models can't. How these quantum feature maps work. Data encoding. Classical data is encoded into quantum states using quantum circuits. This process involves mapping data points to either amplitude or phases of quantum states, creating a quantum representation of data. Quantum circuit design. This design of quantum circuit is crucial. It typically involves a series of quantum gates that manipulate qubits in a way that preserves the relationship between data points while transforming them into a higher dimensional space. Higher dimensional space. The transformation allows for the exploration of complex patterns that are difficult to identify in the original space. The quantum state space can be exponentially larger than classical feature spaces, providing a powerful tool for data analysis. Now let's see the steps. First, classical input. We receive classical data points, x, let's say x. First, we need to represent this data in quantum system and then quantum circuits for encoding. We use gate operations to embed data into quantum amplitude or phases. We design circuits with rotation gates, such as Rx of x, Ry of x, Rz of x, etc. And we use also entangling gates, C0, Cz gates, resulting quantum states. After applying this encoded circuit, the state becomes ket of phi of x. This state lives in Hilbert space, which scales exponentially with number of qubits. Let's see an example. Let's say we have two 2D data points that zero point 0.4 and zero point 0.7. We apply Ry gate on both of them on one qubit. Ry of zero point 0.4, Ry of zero point 0.7. The system evolves into ket of phi of x, that is Ry of zero point 0.4 and Ry of zero point 0.7. We know that when applying any rotation gates, the quantum system first stays in get 0, 0. Because it is 2 qubit, we have get 0, 0. If it is 1 qubit, we'll have get 0. Now this state contains quantum correlation between two features that will be hard to describe classically. Now let's discuss about kernels. Firstly, classical kernel. What is a kernel? A kernel function k of x comma x prime computes similarity between two inputs. Here, x and x prime are two inputs. So k of x and x prime is the inner product of phi of x and phi of x prime. Here, phi of x is nothing but feature map embedding of x. Why use kernels? Data can be linearly inseparable. Mapping to a higher dimensional feature space can make patterns more visible. Examples of kernels are polynomial kernel and Gaussian kernel. Polynomial kernel formula and Gaussian kernel formula. Now, let's discuss about quantum kernel. Once we have encoded data into quantum states, we need to compare these states. That's where quantum kernels come in. A quantum kernel k of x comma x prime is the square of magnitudes of inner product of phi of x and phi of x prime. This measures the overlap between two quantum encoded data points. Here, overlap is nothing but similarity. How do we compute this? We have two methods, direct overlap and swap test. Direct overlap is to run quantum circuits and measure. Swap test is a clever quantum state that computes fidelity between states. Now let's see direct overlap method. In this method, we need to follow below steps. Firstly, we need to define a quantum device with number of qubits and then define the rotation gate, either Rx, Ry or Rz. Here I am selecting Ry gate and then build overlap circuit. As I am applying Ry gate, first I need to apply Ry on X and then I need to apply Ry on negation of X prime. Because I need adjoint of Ry of X prime, I am applying Ry on negation of X prime and then measure probabilities, compute inner product, and then compute quantum kernel. This is nothing but similarity between two states. Now coming to the code. I am defining a quantum environment with one wire. And then I am writing a function to compute Ry of for that given value. And then I am writing a function to pass and calculate Ry. And then I am getting two inputs, x and x prime. X is 0.4 and x prime is 0.7. And I'm applying get state on both of the inputs. As we know, inner product is just dot product of state that is x and x prime. And then I'm getting kernel value that is nothing but square of inner value. And then I'm printing both inner product and kernel value. These are the respective inner product and quantum kernel values. This is about direct overlap method. Now let's discuss about swap method. In this method, firstly, we need to write inner product expression. To write inner product expression, we need to find how the quantum output is behaving on the gate we apply. So, first I need to find out the expression for the gate I am applying. Here, as I am applying RY encoding, I know the formula of RY encoding feature map. That is cos of x by 2 get 0 plus sine of x by 2 get 1. And then I need to write simplified version of analytic expression for inner product. Then I'll get this following expression. And then for calculating quantum kernel, I know the quantum kernel formula is nothing but the magnitude square of inner product. We already calculated the inner product. Now we just need to square the inner product to get quantum kernel. So let's go to the code. Here, as I'm applying RY gate, I calculated the inner product formula is cos of x minus x prime by 2. So I am defining x and x prime values here And then firstly, I am calculating this value as delta. Delta equals to x minus x prime by 2. And then calculating inner product, that is cos of delta. I'll get certain value, that is cos of 0.4 minus 0.7 by 2. That is cos of minus 0.15. The value here will be 0.988. And then for kernel value, we just need to square the inner product. The square of inner product will be 0.977. So the inner product value is 0.988 and the kernel value is 0.977. This can be found out with both SWAT method and direct overlap method. We'll get both same values. As you can see, here the inner product value is same as direct overlap method. Why quantum kernels are necessary? With quantum feature maps, the data is embedded into quantum Hilbert space, ket of phi of x. It has exponential size. Let's say for n qubits, we'll have 2 power of n space dimension. This allows quantum systems to capture richer, more complex patterns, represent entangled nonlinear relationships between features, perform similarity comparisons in spaces that are too large for classical computers. Let's see about high dimensionality data embedding. It is a method of mapping data points from a low dimensional space, such as 2D or 3D, into much higher dimensional space, where patterns, clusters, or relationships become easier to separate or analyze. Why are we embedding into high dimensions? Nonlinear patterns become linear. In low dimensional spaces, some datasets are tangled and impossible to separate with a straight line or hyperplane. But when lifted into higher dimensional space, simple classifiers like SVM can cleanly separate them. And then more expressive power. High dimensional embeddings allow models to access more features, combinations, and interactions than available in original space. Now, kernel trick. Instead of explicitly computing all features, kernel methods compute inner products in high dimensional space implicitly, making computations tractable. Let's wrap up what we have learned. We started by understanding feature maps, the tool that transforms input data into new spaces where patterns and separations become clearer. Then we explored quantum feature maps, where classical data is encoded into quantum features, quantum states, tapping into vast power of Hilbert space. We broke down the steps in quantum feature maps, encode data, apply parameterized quantum gates, generate high dimensional quantum states, and measure overlaps. We saw why we use quantum feature maps, quantum advantage through explicitity and entanglement. Then we compared classical kernels to quantum kernels, which measure overlap between quantum states. And then we unpacked high dimensionality data embedding, where quantum systems naturally lift classical data into exponentially large spaces and enabling advanced pattern recognition. And then quantum feature maps and quantum kernels represent a fascinating frontier that is combining the strength of quantum computing with the power of machine learning to tackle problems we can't solve classically.
And subscribe for more quantum computing videos.